And then, yeah, awesome. So thank you all for coming. I have a lot of content to get through, so we'll get right started here. Hang on 1 second. Yeah, okay. Hang on, I can fix this. So thanks for coming to my talk. We're going to talk about post-mortem debugging in Node.js. First, a little bit about who I am. My name is Thomas, as was said before. I work on a lot of open source software. I work at Elastic, where I also work on open source software, specifically with Node.js instrumentation. And I tweet on Twitter as well, and after this talk I will tweet out a link to the slides. So if there are some commands that I'll show that you can't remember, you can just find the slides on Twitter. I'm also part of the Node.js diagnostics working group, where we work on tools and APIs and Node Core to make Node.js easier to debug and to diagnose problems. And some of these things is what I'm going to be talking about here. So what is post-mortem debugging anyway? It's about getting rid of bugs, right? But let's ask Wikipedia. And Wikipedia says post-mortem debugging is debugging of the program after it has already crashed. That's certainly true, but we have developed a lot of tools to do this. And these tools, turns out, can also be useful to sometimes figure out why things might happen before they happen. So we'll also get into that. So some of these tools is, for example, LLDB and llnode that we'll talk about today. There's also MDB, which people used to use before. LLDB became the tool to use in Node for post-mortem debugging. We'll get into that. There's a lot of other things. Chrome DevTools, you probably already know about that. You can maybe load in a heap dump into Chrome DevTools, or you can connect Chrome DevTools directly as a remote debugger to a running application. You don't want to do that in production, though. So let's jump right into core dumps. I said this word a few times. What is a core dump? So sometimes I find it really useful to figure out, if you want to figure out why something is called something and what it is, to learn a little bit about the history. So for 20 years, before we had rotating hard drives and solid-state storage, we used to store our data on these things. This is a magnetic core plane. You're viewing it from above, and you can imagine there's like several of these stacked on top of each other inside a computer in the 60s and 70s. And if we zoom into it, we'll see some small magnetic or ferrite cores that can be magnetic. And they can have either clockwise or counterclockwise magnetic field, and depending on that direction, it's either a 1 or a 0. So if you run a program on this very old computer and it doesn't behave like it should, how do you figure out the state of the computer? There's no monitor back then. So what you would do is, this is an IBM 1401 mainframe, and this is a 1403 printer, a dot matrix printer. You would print out the content of all these magnetic cores as hexadecimal onto the printer. And that would, let's see, yeah, that would look something like this. And then you really had to work through this and figure out, okay, what's the state of my program based on the memory? It could be tricky, right? But luckily, we've come a long way since then. We still have these memory dumps, these core dumps. That's why we call them core dumps. But we not only have the memory, we also have processor registers, information about that. We have information about the program counter and system flags, a lot of other nice information that we can use. And then we store them in, different file formats. So the oldest one is not really used that much, but the most popular one is ELF. used in Linux, BSD systems, etc. But if you're using a Mac, you'll probably be using I'm not sure if it's called Mac O or Mark O or something like that, but that's the one you use on a Mac. And how does you get a how do you get a core dump? First you have to tell the operating system that you want core dumps, and you use this command ulimit -c and then the size of the core dumps you want to allow to be generated. Because obviously, when a program crashes, the program is crashed. It can't do anything itself, so it has to rely on the operating system to generate this dump of memory to disk. And the operating system, by default, doesn't do this because you will fill up your hard disk in no time every time a program crashes, so you have to run this command. Then when you start Node.js, you need to tell it to actually tell the operating system to generate this file once it crashes, because normally when you have an on-call exception in Node, it's actually not crashing. It's just exiting with a non-zero exit code. So the operating system thinks everything is fine. So you add this flag abort on uncalled exceptions, which will make it send this abort signal to the kernel. And you can also generate a core dump on the fly if you have a running process and you just want to get a snapshot of the memory. You use gcore on Linux and give it the process ID. And on Mac, you'll probably use this command. It's a little bit more complicated, LLDB. You can also use that on Linux, but it's way easier to use gcore. It also generates smaller core files, so it's better. And here you can just specify the name of the file you want it to be output to. So now you have a core file. How do you look into it? Because we could just print it out on a piece of paper, like in the 60s and 70s. But we have some tools now that are super nice that we just talked about. So LLDB is the one you'll probably be using with Node.js. The most common, so by the way, I thought for a long time, like, it stands for database. No, it stands for debugger. That shows you how smart I am, right? But so LLDB is it's cross-platform, super nice. You can install it with Homebrew, or if you have Xcode already on your system, you actually already have it. But if you don't want to install Xcode, or if you maybe want to upgrade to a newer version than the one that ships with Xcode, you can use Homebrew if you're on a Mac, and you can use apt-get if you're on Linux, for example. And what is, so you use that to install LLDB. But LLDB is a general purpose debugger. It understands any kind of dump of memory by any C program or compiled program, right? A Rust program as well. But it doesn't understand JavaScript, right? So for it to be able to understand JavaScript, we need to install a plugin into LLDB, and that's called llnode. And llnode is basically telling LLDB where in memory the different things related to Node.js is, as opposed to the C code that is libuv or V8. Because it understands all the libuv and V8 stuff and the Node C++ code, but it doesn't understand the JavaScript code. So this is what llnode is about. So the way you run this debugger is you just give it the path to the binary, and this is important. You need both the core file and the binary of the program that crashed, because when the binary is compiled, a lot of information is actually compiled into the binary about how the memory structure looks and stuff like that. So if you just give the core file to LLDB, it doesn't know how to interpret the core file. That's why you need the binary, and that's why the binary needs to have these extra metadata compiled into it, which all binaries today, like normally when you compile a binary, that's included, and it's also included in Node. So you need the path to the Node binary and the path to the core file. And then when you load LLDB, you then need to load llnode, but it's much easier to just use this shortcut llnode, and we'll set up the plugin for you. Takes the exact same arguments, and there we go, right? So let's talk about crashes. So this is probably the first time you'll ever encounter a core dump when you have a crash. And normally when you have a crash, you'll just look at the stack trace. And hopefully the stack trace is sufficient to figure out what's going on and why you're there. And as we just heard from Ruben previously, if you were here for his talk, Node now ships with async stack traces if you're using async await. So the stack traces will probably be much easier to debug, but maybe you're on a system that doesn't run that new version of Node, or maybe you're just using code that is not using async await. So you have this stack trace here that comes from some next tick, and you're like, okay, but how, why, how did it get there, right? We start up our server with this abort and uncaught exception flag. That runs, and we send a request to it, and then we see this. You can see right there in the bottom there, it says that it generated a call file, if you do this on a Mac, there we go. It will be stored in /cores, and then the core dot the process ID of the process. And first we'll look at this error message. So cannot read property final first of undefined. Okay, that tells us something. Then we look at the line and we see, okay, this is app server line 16. Okay, so let's look inside that. We can see line 16, that's actually number 4 in this screenshot here. Cannot access first and undefined, so that's so some name is undefined. A user.name.first of name somehow is undefined. But why is it that? Okay, if this was locally in development, we'll just add a console log statement and we'll be done. But if this is production, this might only happen once every month, and we don't know why. So we can get access to the core dump of this, and this clicker is really random. We can get access to the core dump of this, and then we can see what's going on, right? So I loaded up a core dump here, and I'm running inside llnode. I did this beforehand because it takes a little time to load up. So I didn't want to bore you with that. And if we write help, we can see a lot of help about which commands we can run inside LLDB. But we loaded the V8 plugin, right? The llnode V8 plugin. So we could write V8 help. And then we get a specific help for the Node.js related things. And we can see here there is a bt backtrace command to show us a stack trace of where the program was when this core file was generated. If we just write bt like this, we'll actually not get the backtrace from llnode. We'll actually just get the normal backtrace without the plugin. So if we scroll up here to the top of the backtrace, we can see like the last thing it did was it sent the abort signal, right? But there's some C code here in Node land. In the bottom, there is also some C code and some V8 and stuff like that. But in the middle, you see there's just blank stack frames. Why are they blank? Because this is all with the JavaScript. And we can also see that the memory address here in the left column, the memory address is very high compared to the memory address of the C code, because the JavaScript code, of course, lives in another place in memory. But we can write V8 BT, then we get the V8 optimized version of the stack trace. And now we can suddenly see the JavaScript stack trace here. We can see we have a function called unsave, and we can see the memory reference to this of this function, and we can see it took 2 arguments. The first argument was null, and the second argument was an object. So let's and if we remember, then the user.name.first, the user object was actually came from the second argument. So we can just copy. This memory address. And then we can say V8 inspect, and then that memory address, and we can actually see here the objects, and it has one property called NMAE. So as somebody spelled name wrong, right? And we can even We can even go in and we can copy, so that points to another object. We can copy the memory address of that object, and we can inspect that, and then we can see that it contains two properties, first and last, as we expected, with the values Thomas and Watson, right? We can also go up here at the stack trace. We can see here, it was frame number 6, so we can say v8, frame select 6. So now we select frame number 6, and we see some, what looks like assembler code. I think then it's v8 source list, I think it is. Yeah, so there we go. Now we actually see the source code. How come we see the source code? I mean, this is a core dump, right? Well, it's because, of course, it's JavaScript. And in JavaScript, the source code is in memory. It's not compiled, right? So we can just view the source code of our application here. So there's a lot of cool things you can do with this core dump. So now we know why the program crashed. So another problem, instead of crashes, can be an unresponsive process. The process hasn't crashed, but it's just not doing anything. It's just hanging, right? So you ask yourself, what is your program doing right now? And again, core dumps can help you. So we have a program like this. It just takes an object and it takes loops over all the values inside the object, and or all the properties inside the object, and each value it will stringify the value, right? So I ran that. There we go. I ran that, and I generated a core dump from it. I'm not going to do that now, because it takes 5 minutes. So, but I loaded up the core dump here, and of course, to figure out where it was stuck, where it was hanging, I just say v8 bt for backtrace, and I get the backtrace or the stack trace of what it was doing, and we can see the frame number 1 up here is the function stringify, right? And so if I say v8, frame select 1, v8 source list. We see the source code here for the function where it's hanging somewhere. So notice that we just get the function. We don't know exactly where in the function that we were stuck. But if we look a little bit at it, we can see we're iterating over some keys in an object, and we're doing that until there's no more keys, right? But the way we check if there's no more keys is we check if key is null. Or not null, right? But unfortunately, when there's no more keys, it's going to be undefined, which means that this will just spin forever, because it will never be null, it will be undefined. So we just change from null to undefined. Our infinite loop will go away. So an alternative to that would have been CPU profiling. If you do CPU profiling on a process and ask the CPU, for example, 99 times a second, what are you doing, what are you doing, what are you doing, you basically get a lot of stack traces back, and you can use those stack traces to actually see the same thing. So CPU profiling would have been a really good alternative to this. So to recap, I'm not going to necessarily go that deeply into these slides, but these are also just so if you look at the slides later, you can see all the commands. But you either run gcore or LLDB to generate the core dump on this running process, and then you start llnode with the commands we saw before, and then here is some you can write frame select and v8 source list and v8 inspect, etc. So this is, I have to press very lightly on this clicker here. So there we go. Memory leaks. That's always a fun one and super hard to debug, right? So what can a memory leak be? Well, suddenly you get this error. Node.js is run out of memory, crashed. And of course, then if you set up your system to generate a call file, you can view the call file, but that doesn't really help us. You can look into the memory, but actually, before we go into that, let's look at what memory leaks are. So in Node.js, it's a garbage collector language, and there's always be one root node, and all other objects in memory will be referred to from that root. This here, when suddenly one node loses a connection, there's nobody pointing to it, that's not a memory leak. That just means, okay, nobody's pointing to me, and then the garbage collector can clean it up. So that's not a memory leak. What a memory leak is if suddenly you have something, it could be an array, for example, or it just keeps on growing and growing and growing and growing, and you never clean this up. Maybe that's intended. Maybe you're just processing a lot of data, but it might be a memory leak. But the problem is you can't tell it programmatically. You can't like have an algorithm that sees that this is a memory leak because it depends on the program, right? So we need humans who understand the code and what the program is supposed to do to inspect this. So we're in llnode here, and we use another command we haven't talked about called find.js objects. So it looks through an entire heap and looks for all the JavaScript objects in the heap. And it lists them out like this. You can see the total size and the name, and it's all listed. And if we go all the way to the bottom, it's sorted by with the ones that appear most at the very bottom. We can see there is one called visit, an object there that appears like 235,000, like 250,000 times in memory. So it's like, I know as an application developer, it shouldn't appear that many times because this is supposed to keep track of the active visitors on the website, and we don't have 250,000 active visitors currently. So there's something wrong here. We're somehow not clearing these up, right? So we can use the same command and say we want to just look at visit here. And we see a lot of visit objects. This is just all of them. 250,000 on them. Then we can select one of them. So just take a random one, take this one, take the memory address of that, and we use the inspect we saw before. We use the -m here to also see the map of the objects in JavaScript. Objects have hidden classes, and that's basically the memory address of the hidden class. We will also see that. So we can see here, and we can reference the memory address of the hidden class as well, and say, okay, that's here. Let's try to inspect that. And then we actually see the hidden class in memory. So this is one of those visit objects, right? But okay, this is not what we're looking for. We're looking for references to the visit object. So we can also use find refs. And find refs will, show you all the references to the visit object. In this case, there's only one, and it's an array, and it's quite large. So unfortunately, right now, llnode is not clever enough to show us where this array actually exists in our code. So we have to do a little bit of manual hunting. Maybe this can be approved. Somebody can make a PR. But maybe the process itself can be improved, because it was a little tedious. What I really would like to see is that, what if you could take a core dump and convert it into a heap snapshot? Because if you have a heap snapshot, first of all, it's much smaller. Then you can load it into Chrome DevTools, and you can start to inspect it in there. It's a much nicer UI. That's a little bit down the road. Nobody's working on this yet, but it would be a fun project. Alternatively, you can trigger a couple of heap snapshots manually. You can configure your Node application to just generate heap snapshots when you send it a signal. And then you can do what's called heap dump diffing. And heap dump diffing is where you take a snapshot at one point in time, and the array at this point is a certain size. Then you wait an hour or 10 minutes, depending on how fast your memory grows. You take another heap snapshot, and you can see, okay, now at a different point in time, the array size is larger. Then you figure out what's the difference between these two heap snapshots, and then you say, okay, this has grown tremendously, this array. And then you can find the common ancestor like we did before, or even better, because this is a heap snapshot, so it means you can do it in Chrome DevTools. And it can point you directly to the object that's retaining these references. So how would we go about doing this? So you could just add this function or this listener to your Node application today. It listens on a user2 signal. So you can send a user2 signal to the process from outside the process. And then it uses a brand new feature that just landed in core in version 11.13, which allows core itself to write a heap snapshot. It used to be that you needed a third-party npm package called heapdump to do this. Now it's built into core. And so you send this, you send kill sig user2 and then the process ID of the process, and that will trigger this function. And then that it will write it to disk and it will return this function here, write heap snapshot, will return the name or the path of the file that's been written to disk. And then you can load it into Chrome DevTools. Have any of you tried to load a heap snapshot in Chrome DevTools? 1, 2, 3, 4, 5. Okay. So in the left-hand column, you can load as many heap snapshots as you want. Just load the file in. So you load the two that you're taking at 2 different points in time. Then there's a drop-down up in the top. I know you can't read the details here, but that's why I made the big arrows. But there's a drop-down up in the top where you say, I want to make a diff of these two. So you put it into what's called comparison mode. And then there's a column here. So the table just below this drop-down shows you all the objects, a group by type. And there's a column where you sort by the delta count of this diff. And then below that, there is all the, you select the one you're interested in, and below that, you see all the references to that. And we can see here, we found an array here, right? It's a little bit, you still have to hunt, because sometimes you might see, okay, there's 2 million strings. Like, yeah, okay, but maybe that's okay. And these strings are all over the place. So you have to use your knowledge of the application and of the source code to do this. But this is currently probably the easiest way to do it. So there's a recap slide. I'm not going to go over the details there. I think the final thing I will do is try to speak Dutch. And I will say, bedankt.